One. Welcome. Okay. My name is Neil Hunt. I'm the Chief Product Officer at Netflix. I've been there since 1999. I've had the opportunity to go through two different complete renovations of the technology since 1999. One was the migration from what I'll characterize as a prototype system in Visual Basic to Java, and that lasted us for about a decade. And then another as we sought to embrace the cloud. We're going to split our talk into two pieces. I'm going to talk about the challenge in front of us, and then Yury's going to step on the stage and talk about how we actually delivered that. But I'm going to kick you off with this. How many of you have ever woken up or actually been woken up to this picture in your life? Hopefully not many. I can tell you it's a pretty scary proposition. We had a major database corruption driven by a hard disk failure, driven by a firmware update that corrupted our Oracle database, cost us about 3 days of the ability to ship disks in August of 2008. And it was definitely traumatic. But it was the stimulus for us thinking about how do we get to the next level of availability and robustness and resilience. And hence, how do we migrate to the cloud, make that work? And so let me give you a bit of context here. In 2008, Netflix was a business in transition. The old business was a DVD shipping business where customers got their value by having a DVD at home. And if the site was down early in the morning or for an hour or two, it wasn't a catastrophe. But in 2008, we had launched the streaming service, and at that point, it was an adjunct. It wasn't very big, but it was clearly growing rapidly. It was clearly the future. And for a streaming customer, if the systems are down or not available, it's a catastrophe. You can't receive value, and you're likely to cancel the service and quit. And so this was a big problem for us. So we saw a need to get more robustness, to reinvent things in a way that the cloud looked very attractive for. So I set out 3 goals for a cloud migration initiative. And those 3 goals were availability, scale, and performance. I wanted us to get to an availability of 99.99%, so that 99.99% of the time a customer tried to use Netflix, it just worked. And that was about 2 more nines than we had at the time in 2008. And that was a huge step up. It was going to require building redundant data centers, making hot spare oracles with hot swap. It was going to require a lot of work, and we thought that rather than do the work on the legacy traditional systems, let's move forward into the cloud. I wanted scale. At that time, every couple of years, every 2 to 3 years, we'd have to completely redesign each component to get the kind of improvements in scale, a magnitude more than we'd designed it for originally. And that was expensive. I didn't want to keep doing that. I wanted to be able to just keep adding instances horizontally. So the scalability was really important. And then to be able to provide a cost-effective, unlimited compute to be able to deliver the answer that customers wanted, that was really the 3rd goal. So availability, scale, performance, that's what we were seeking. That's what I was trying to deliver here. The big challenge, how to get there. On the left, the old model, a monolithic app, replicated, talking to a single Oracle instance. On the right, a replicated NoSQL database, with a service-oriented architecture, how to get from one to the other without taking 2 years off and not delivering value to customers. And I want to switch to an analogy here, which I think is an important one, and it's something that actually has a lot of resemblance to the real problem we're trying to solve. The old-style architecture felt to me a lot like an 18-wheeler truck that we owned. It's big, it's reliable, it's efficient at delivering a full load, but it's expensive. And its inflexible capacity is not very good at delivering a half a load or 1.5 loads. And it's actually not available all the time either. It's down for the driver to get sleep. It's down periodically for maintenance and service. And unless you have 2 or 3 of them, having full availability is hard. And it has many single points of failure, from a flat tire to a sick driver to congestion on the highway, all of which are catastrophic. And the new style, the model I want to get to, is more like a fleet of pickup trucks that you lease. And the idea here is that it's scalable to small or large loads at any level. It's reliable through redundancy. You don't expect every single truck to always get there, but you break up your load in a way that as long as most of them get there, you're in fine shape. And if you've got a sick driver, if some of the trucks get a flat tire, if some of the routes the drivers choose to take end up with congestion, you're still going to be able to deliver the right answer at the right time. But it requires rethinking the whole problem, reformulating an architecture that's appropriate for a completely different structure. So the first question we faced as we contemplated that, what does this new architecture look like, was the question of should we stick with a SQL database or should we switch all the way to a NoSQL solution? And we obviously weren't going to use an Oracle database. We had already bumped up against the exponential price increase for increasing size of Oracle. And in order to get the availability we needed, we would have needed to have built hot spares and hot swap and hot failover, all of which was going to be quite complicated, and which MySQL did better at the time. And so my developers, on the one hand, had a lot of familiarity with programming to SQL. They saw transactional consistency as an important issue, and the NoSQL stuff felt like it was going to make that job much harder. And so there was pull on that side. On the other side, the opportunity for that unlimited horizontal scaling made the NoSQL solution seem very attractive. And avoiding the overhead and risk of managing SQL, of managing downtimes for backups, of managing downtimes for schema changes, things like that. All of those things we wanted to get away from. We couldn't agree, so we ended up experimenting and doing a little of both. We built some persistence on SQL and some persistence in Amazon's SimpleDB. And in the end, neither was the right answer. The MySQL stuff worked, but it wasn't the solution we were looking for. And the SimpleDB didn't have the availability and performance that we needed. So we ended up throwing away all of that stuff and switching to Cassandra. Actually, the migration from SimpleDB to Cassandra was relatively straightforward, happened pretty quickly. We put a lot of work into Cassandra, but Cassandra offers us a lot of the flexibility of scale, of multi-region replication, of the failover and redundancy, all of the attributes we were looking for. So that's clearly the right answer, looking back on it now. The next question we struggled with is what exact kind of architecture do we want to build on top of that? And I was convinced I wanted to shift to a service-oriented architecture, starting with the persistence layer, layering simple self-contained services on top of that in layers all the way up to a presentation layer that assembles for delivery to the customer. And the advantage of this, the key win, the key benefit, is that we get away from a monolithic team of all the developers having to coordinate around a Tuesday push cycle where all the code gets integrated into one big push, which inevitably resulted in the Tuesday push becoming the Thursday push or maybe next week's push, or some feature of importance getting left off the train because it was broken and couldn't be made to work in time. That was the old model. In the new model, the developers are focused in small teams of 6 to 12 people around a single component. And they can move that component forward on their own schedule. And if there's a necessity to deliver a new version of that component with new features for some other dependencies, we can have the new and the old running side by side in the cloud. So lots of flexibility, lots of developer efficiency coming out of this new kind of structure, but something that required us to sort of rethink and not just forklift the old code into the new. So how to manage the migration? On the left, where we were at, on the right, thinking about building up 1 or 2 small components of the system we wanted to have. We needed to be able to serve some customer requests out of one side and some out of the other side, and how to be able to do that. And in order to do that, Kevin coined a phrase called Roman riding, representing the challenge of trick riding on 2 horses at once, one horse being the old infrastructure, the other horse being the cloud infrastructure. Of course, that's a risky proposition and requires a lot of work. But it was an important piece of building transitional infrastructure to be able to navigate from where we were to where we wanted to be. 3 variations that we use for different kinds of data. In one variation, we took the source of truth, the master, from the Oracle database and made a read-only copy in the cloud. An example of this is the membership records. The initial pieces of technology we wanted to bring up in the cloud during this migration were the movie players, and the content browse and search stuff. All of that needs to know whether a visitor is a member or not a member, but doesn't need to be able to change or manage that data. And so by creating a read-only copy in the cloud, we were able to build those pieces of technology, test them, deploy them, understand how they work, learn what we needed to learn, and then move on to the next step. And this was the solution that made that real. In other cases, we were able to get further ahead, and we were able to build a system with the source of truth, with the master copy in the cloud right from the get-go. And an example here is our A/B testing infrastructure. A/B testing is the process of providing different groups of customers with slightly different experience in order to be able to evaluate which one works best for the consumer. And the mechanism here is to distribute people is to tag people's accounts with an A or a B tag that delivers a slightly different experience to each member. And if we do the test allocation and distribution in the cloud, make that the source of truth, and then copy those tags across to the original data center infrastructure, we're actually closer to the place we want to be at the end of the migration. So this was an incrementally better solution where we could make this happen. But sometimes we needed to build the full multi-master replication between the old infrastructure and the new for supporting this transition. And the example here is the data structure supporting the queue. And the queue is the list of movies that people want shipped to them on a DVD, or the list of stuff they want to watch in streaming. And we felt that that was such an important thing that was important on both the old and the new during this migration, that we really needed to have a multi-master copy. And so we built a considerable effort, this copying back and forward between heterogeneous representations of the same data. And I have to say, it was relatively it was a mistake, and it was relatively complex. In retrospect, what we should have done is to do the second solution, building a source of truth in the cloud, and instead having a proxy in the data center to capture the writers in the data center that would have been writing to the SQL database and copy that across to the cloud and have it copied back again. Would have been a better solution, would have been more scalable, more simple. So this was one of those experiments that we built, that we learned, that we ended up discarding. We ended up discarding the whole initial implementation of the queue representation and the queue transitional infrastructure here to build something better down the road. I didn't only want to bring the technology from the old to the new. I wanted to bring the team with it, too. I wanted to take the team that was well experienced in building the kinds of applications we had prior to 2008 and make that team proficient and effective in delivering architectures in the cloud. What we did was we took the opportunity to hire new individuals with experience in this kind of technology, although not specifically in AWS, since it was pretty new in 2008, 2009. And those individuals were able to see the kind of transition that I needed from the rest of the team that was experienced in the old technologies. And we gradually, team by team, stopped people working on the legacy infrastructure and started them working on the cloud, moving the technology across piece by piece until now we're essentially all working in the cloud. But then the second key piece here of the organization was the IT ops team. And we had a very traditional developer team and a separate IT team that supported the hardware and the firmware and the patches and the data center and the footprint and the power and all of the stuff that IT organizations do. And as we moved to the cloud, we saw much less need for that kind of stuff because fundamentally we were building against components at a much higher level of abstraction. We didn't need to worry about data center footprint or power. We didn't need to worry about firmware revisions or operating system levels on the servers because AWS manages that all for us. And so the advantage of having devs take on the responsibility of operating their applications instead of passing that off to IT ops is that A, they don't have to take care of those low-level details, and B, they're strongly incented and able to build the kind of automation that makes the stuff just run. So automation at push, automation at scaling, automation for monitoring and automatic healing and fixing of issues that come up. And if you have a human in the loop, it's very, very hard to get to 99.99% availability. If you've got automation in place, it becomes feasible to achieve that. And so by focusing on the DevOps model, I think we're able to get much closer to building towards that level of availability. The journey we took then, I've summarized, I'll summarize the steps we've taken and we are taking. 2008 was the stimulus. 2009, we seriously got going on this stuff. And we did some pilot projects, basically bringing the streaming player into the cloud. And we made some pretty diffident steps at first. We launched this for 1% and 5%, 10% of customers, and we pulled it back to the data center for a bit, and then we launched it again in the cloud. And it took many weeks to get to a level of stability and performance where we were happy with it. And over a period of months, we gradually moved more and more stuff across. In 2010, we were happy enough to embark on a full-scale project to move most of the member experience, that is the players and the browsing and choosing and search. All of that stuff comes across to the cloud. And in August of 2010, about 2 years after the initial failure in the data center that caused us to want to move over, we actually launched our iPhone 3 application, which was the first app that was supported exclusively out of the cloud, had no data center fallback. And I can tell you that for Yury and Kevin and some of the others, that was a nail-biting day as we launched that high-visibility application with no fallback to the data center. But it worked, and we were in good shape. And then we moved on over the last couple of years to migrate the e-commerce and membership experience over to the cloud. So essentially, almost everything is in the cloud at this point, with the exception of the payments mechanism, which is held back by some PCI and SOX constraints that we hope to solve and migrate next year. So that's the journey. I want to sum up my portion with 4 lessons that I've learned, which hopefully will be valuable to some of you as you contemplate a similar project. Lesson 1 is embrace the whole concept and don't be tempted to forklift existing applications based on old architecture and old assumptions into a new cloud framework. Really embrace the idea that these things need to be rewritten to take advantage of the commodity computing and to leverage the resilience available by constructing an architecture that's resilient through redundancy. You know, we had lots of opportunities to exercise the old versus the new and see that embracing the whole concept was the right thing to do. Plan to discard your first experiments. The first attempts we made, we learned a lot from, and in particular, exploring SimpleDB was a powerful learning tool. We ended up throwing away all of the work we'd done on that and moving to Cassandra instead. A number of other things got tossed out along the way. So by taking this incremental approach of piece by piece, you get to learn lots of stuff on the way before you've committed whole hog to it. And then you get to throw it away, rebuild it, and then take those lessons forward as you migrate the rest of the application forward. Do invest in transitional infrastructure. It's so important to be able to move piece by piece and not have to move the whole thing all at once. The transitional infrastructure, the Roman writing, the data propagating between the old and new in a way that means that you can run part of the application in the old and part in the new at the same time. That was hugely important to us. And then finally, expect your team to learn new ways, new techniques, new ideas. That is what we were able to accomplish. But be aware that some won't necessarily be able to make the transition, so it's important to be able to upgrade the team along the way. And that's something that we keep pushing on. I will introduce Yury, who's going to talk about how we fulfilled on the promise here.
Well, thank you, Neil. My name is Yury Izrailevsky. I'm VP of Engineering at Netflix. So as we move to the cloud, Neil has set the top priority for our engineering team to focus on scalability, performance, and availability. So cloud is the foundation of our infrastructure. It requires us to do things differently, but at the same time, it provides us with some unique capabilities that allow us to build software that's more scalable, performs better, and more reliable than anything we could ever build in our own data center. So let's start by talking about scalability. In the last few years, our streaming product has undergone tremendous explosive growth. As you can see from this graph that tracks weekly number of streaming starts from the beginning of 2009, in less than 4 years, our streaming usage has gone up by nearly 2 orders of magnitude. And beyond just the long-term growth trends, we often see short-term spikes, for example, around the holidays, where streaming usage goes up by 50% or more in just a matter of a few days. So supporting that kind of explosive growth would never be possible in our own data centers, where hardware provisioning cycle takes many weeks, sometimes months. Benefits of cloud scalability become even more apparent if you look at our cross-regional cloud architecture. So we're supporting our US, Canadian, and Latin American customers from a single cloud region in US East in Virginia. But earlier this year, we've expanded into Europe. In January, we launched our service in UK and Ireland, and just last month, in October, we've expanded into the Nordics. And in order to provide our European customers with low latency interactive experience, we've spun up a new cloud region in EU West in Ireland. And we're synchronizing the two cloud regions using Cassandra replication. Well, if we were to spin up a new data center in Europe, or any new country for that matter, we would need to provision colo space, buy and rack up hardware, set up networking, put operations teams in place. It would take many, many months, and it would be a significant upfront investment of tens of millions of dollars. And with the cloud, we were able to spin up our initial deployment in this new cloud region in just a matter of a few days. And because we didn't have a lot of European customers to begin with, we could go with very small deployment that cost us next to nothing, and then gradually grow it as our streaming usage increased in that region. In addition to cost benefits, we also realized a lot of availability benefits with this cross-regional approach. So for example, we've seen failures in our US East region, but our European customers were isolated and continue receiving service with no interruption. And going forward, we're looking at some cost-effective ways to redirect customers from an affected region to the other one, so that all of our customers will continue receiving Netflix service, even if an entire cloud region goes down. And as we grow and expand into different regions and become a truly global company, present all over the world, we have the advantage of being able to rely on all the different cloud regions that AWS provides, so that we can provide our customers with low latency interactive experience and high degree of availability wherever they happen to be in the world. Now let's talk about performance. So as we decided to move into the cloud, saving money and reducing costs was not our primary motivation. We were mostly concerned about scalability and availability. However, as we built our cloud architecture out, our current cost per streaming start in the cloud is much less, is a small fraction of what it was in the data center, and it continues to go down. In fact, if you look on this graph that tracks cost per streaming start, over the past year to the end of Q3, it's gone down by more than 50%, and it continues to go down. So what are some of the ways that we're optimizing our cloud efficiency? Well, we're primarily focused on tools and automation. At Netflix, we really believe in the culture of freedom and responsibility, where each engineering team is responsible for their own architecture, they manage their own releases, their deployments, and there is no top-down heavy process that dictates to them how they should do things and what their architecture should look like. Instead, we build tools that give everyone the visibility into what each team and each component is spending in the cloud. And we also provide tools that increase efficiency for everyone. So for example, we've built Janitor Monkey, which scans our production deployment and automatically cleans up unused capacity. EC2 instances, auto-scaling groups, ELBs, security groups, and so forth. We're also developing the Efficiency Monkey, which uses machine learning techniques to optimize underutilized capacity. It looks for bottlenecks in CPU utilization, memory footprint, thread pool allocation, and so forth, and optimizes our efficiency across the board. And in order to save money on storage costs, we've also developed automation that cleans up old data, and we're also taking advantage of things like object expiration in S3. So another opportunity to optimize our cloud efficiency comes from the fact that our usage is very cyclical. So as you can see from this graph that tracks our daily usage, it peaks around 7 p.m. and it drops off by about an order of magnitude in the middle of the night. So when we used to provision our cluster capacity statically for our peak usage, there was a lot of unused capacity during the troughs. So in the past year, we've been aggressively moving to load-based autoscaling, where the size of our clusters grows and shrinks with our streaming usage. And as you can see from this graph that tracks hourly usage for one of our production clusters, before and after we moved to load-based autoscaling, our costs immediately were reduced by more than 50% with load-based autoscaling. Now let's talk about availability. So our goal with the Netflix product is to build world's best streaming product. And that requires a lot of things. Appealing content, great UI, personalization, but at the end of the day, the service just has to work. Think of your lights coming on when you flip that switch, or the cable box that just works when you turn it on. So availability is really fundamental. And as Neil mentioned, our goal is 4 nines of availability, which means that on any given week, we can afford to be down at most 30 seconds during our peak traffic. Well, how have we done against this goal historically? So as you can see from this graph, it tracks 13-week moving average for our streaming availability. And in general, the trend has been upward. In fact, we were able to add roughly another 1 9 of availability over the last 18 months. Of course, you'll notice a big drop here, which corresponds to the outage that we had on June 29th, earlier this year. So it started out as an EBS, Elastic Block Storage Service failure in one of the availability zones in USC's cloud region. But it was really the inadequate performance of our own fault tolerance and redundancy mechanisms that allowed this outage to affect our customers and persist for nearly 3 hours. We can and we should be able to do better than that. So cloud is all about building highly reliable systems out of fundamentally unreliable hardware and software components. And there are best practices that we can employ that would allow us to survive any kind of failure, whether it's hardware failure in AWS or our own software failure, and not affect our customers. And in fact, in the last year, there have been several other similar AWS failures that we were able to survive with no impact to our customers. It's all about the redundancy. So what are some of the common failures that we see in the cloud, and what are we doing to survive those failures better? So as Neil mentioned, we're building loosely coupled distributed infrastructure in the cloud, where there are multiple components running side by side on different clusters, talking to each other through RESTful interfaces. So what we often see is a cascading failure of those components. So consider this real-life example that happened some time back, where we've seen all of a sudden a spike in SimpleDB latencies, which brought down our instant queue service in the cloud, which impacted our API service. And as a result, some of our devices could not stream on Netflix. So this is a fairly typical example of a cascading failure that affects 3 components in the cloud. Well, if you look at our overall architecture, we have more than 300 components running side by side. And each one of them is a distributed service of its own, running on multiple instances. So if we depend on the availability of each and every one of these components to stay up, and let's say the availability of each one is 99%, the combined availability of the system is 99% to power 300, 4.9%. Basically, we would always be down. So somehow, we have to build an architecture that would survive the failure of one or multiple components without bringing the whole system down. So we have to be stronger than our weakest link. And there are really two main strategies to achieve that in the cloud. One is graceful degradation, and the other one is complete redundancy. So graceful degradation basically means that if one of your dependent components fail, rather than bringing the whole system down, you degrade some of your functionality while keeping the rest of the system operational. So for example, if our movie personalization service fails, rather than failing the whole site, we just drop the top 10 row for Yury, and we show popular titles instead. And the rest of the system continues to work. And of course, complete redundancy is critical. We deploy all of our systems across 3 different availability zones. So if one of them goes down, we can continue serving our customers from the other 2. And when it comes to our customer and production data, we have additional levels of redundancy in order to ensure data availability and durability. Each data element, we store our data in Cassandra, and each data element is replicated across 3 different availability zones. And that protects us against hardware failures. And to protect us against logical failures, such as software bugs or operator errors, someone accidentally drops a column family, we run regular backups of all of our data into S3. And then to protect us against natural disasters affecting the entire cloud region or catastrophic security breaches, we run a secondary backup of all of our production and customer data into our heterogeneous cloud environment. So we have 3 different types of redundancy built into our storage infrastructure to ensure availability and durability of our data. So all of these are great best practices that can help us design and build fault-tolerant architecture. But just designing a fault-tolerant system is not enough. You constantly have to test your ability to survive those failures. Just imagine getting a flat tire. You might have a spare in your trunk, but is it inflated? Do you have the tools to change it? And most importantly, do you remember how to do it right? Well, one way to find out is once a week you poke a hole in your tire and you go through the drill. And this is exactly the approach that we used when we've developed Chaos Monkey, which is a tool that goes and randomly terminates production instances just to test our ability to survive those failures. We've also developed Latency Monkey, which simulates network outages just to test our Graceful Degradation. And we have Chaos Gorilla, which simulates an outage of an entire availability zone. And Chaos Monkey and the Simian army have been extremely helpful for us in ensuring our fault tolerance. So earlier this year, we've open sourced it to the wider community. And it's been getting a lot of traction. In fact, over the past year, we've open sourced over a dozen different projects, and you can access all of them at netflix.github.com. In the past, we've benefited a lot by incorporating a lot of open source software into our own systems, and we wanted to return the favor by sharing what we've developed. And we also believe that by combining what our engineers produce with the best minds out there, we can develop systems that are much better than what we could ever develop by ourselves. And it also has some other benefits for us. It helps us with recruiting, and we're always on the lookout for great talent out there. And it also happens that engineers just write better code when they know that lots of other people will be looking at it. So it's a great open source effort has been great for us, and I hope that you will be able to benefit from it as well. And in fact, Ruslan tomorrow will have a whole session dedicated to our open source effort. A few weeks ago, Superstorm Sandy landed on the East Coast. It was a devastating natural disaster that affected a lot of people. Schools and businesses shut down. A lot of people were stuck at home. And perhaps not surprisingly, many of them turned to Netflix. And in fact, we've seen that our usage on the East Coast, main metropolitan areas there, Boston, New York, Philadelphia, Baltimore, DC, spiked by more than 2x, more than doubled in the days immediately following the storm. And of course, we're happy that we're able to provide at least some comfort to the people affected by the extreme weather. And even though in anticipation of the storm, we had all of our resiliency and fault tolerance infrastructure on high alert, we were pleased to see that AWS infrastructure in Virginia held up, and we did not need to use that fault tolerance system. And we're also pleased that the scalability and availability of the cloud allowed us to scale and survive this unexpected spike in streaming usage without any degradation of service for our customers. And at the end of the day, our goal is to build world's best streaming product, And we're very happy to partner up with AWS, who are doing a lot of heavy lifting for us and are helping us achieve our goal. So with that, just wanted to thank all of you for the opportunity to talk to you about our experience. And just to let you know, there's a number of other Netflix presentations at re:Invent this year. I hope you got a chance to catch the keynote with our CEO, Reed Hastings, this morning, and hope you'll check out some of these other presentations as well. And with that, Neil and I will be happy to answer any of your questions.